Okay, so thank you for inviting me. So I will start with the statistical context actually, and we'll go back to the exoplanets after that. So let's consider a very simple problem where you have n hypotheses. So let's number them, let's call them hi with I from 1 to n, and you have some data y, and you want to know which of the hypotheses are true. And so there is a paper by Müller et al. Here, which wants to, so basically if you say that hi is true while it's not, it's a false positive. And if hi is true, but you didn't say it was, it's a false negative. And you want a detection criterion which minimizes the expectancy of false negatives plus a certain cost times the expectancy of false positives. And you can show very simply that the optimal procedure is simply to take the hypothesis with the highest posterior probability greater than a certain threshold. And then you can also control very simply the false discovery rate. So the expected number of false detections on the total number of detections is given by this very simple formula. And which links this sort of decision theoretic approach to the Benjamini-Hochberg approach to false detections. And what I'm going to talk about here is, okay, but now let's suppose that the hypotheses, they are not discrete anymore, they are continuous and they are indexed by regions of the parameter space. So the problem that I have is that I have a data set which is described by parameters, by patterns. These patterns, they all have the same parameters. And I'm going to say, well, I have a pattern with parameters in this region of the parameter space. I have another one there. Maybe I have a third one somewhere else. And then each hypothesis, I have a parameter there, is parameterized by this region of the parameter space. And basically what I want to know is if this reasoning still holds. And this problem emerges from the detection of exoplanets. And so now let's take a turn to astrophysics. And so what is an exoplanet? First, let's define a planet. So it's a celestial body at hydrostatic equilibrium. So basically it's round. Its own gravity is sufficient so that it's round, and it has cleaned its orbit around its star so that it's a sort of loose definition, but it's an official definition from the IAU, which means that there's nothing else. There's no other significant body in the same orbit as the planet, and in the definition of a planet, it's that it orbits the sun. So here you see in the representation semi-major axis, so distance to the star and mass. In here you have the planets of the solar systems plus Pluto. So Neptune, Uranus, Saturn, Jupiter, the Earth, Venus, Mars, and Pluto. No, that's Mercury. That's Mercury, sorry. So Pluto is not on this graph. Okay, so now if you take out the condition that it orbits the sun, you have an exoplanet, and we have over 5,000 confirmed exoplanets as of today. So here is a representation of the different exoplanets known. Each point is an exoplanet. So these are individual planets, but of course, if you look at a particular system around a certain star, you might have several planets. Here is an example of system with 5 to 6 planets. Orbiting the star, and the orbits of the different planets are represented by the black circles. Okay, so you have different colors on these graphs, and what do they correspond to? So each color corresponds to a different detection method. And you have several observational methods to detect exoplanets. The first one, and probably the most known, is transits. It means, so the principle is very simple. If you have a planet orbiting the star and you observe the brightness of the star, if the planet passes in front of between the star and the observer, then you should observe a decrease of brightness, which repeats periodically each time the planet goes around the star. Now, you have another popular method, which is radial velocity, and which is the main object of my talk today. So the principle is that if you have a planet orbiting the star has a reflex motion, and the observer will see a Doppler shift of the star moving back and forth toward the observer. And thanks to this Doppler shift, you can measure the radial velocity, and if it has periodic variations, then you can see that there is a planet orbiting the star. You have another technique which is called microlensing, which is, so when you have the observer here and two stars which are aligned for a moment, the star in the middle passes in front of the background star, then the light of the background star will be amplified with a relativistic effect called microlensing. But if there is a planet orbiting the star which passes in between the background star and the observer, then the magnification will have a certain bump here, which is characteristic of the presence of a planet. And now another popular technique is the imaging one. And in the imaging technique, this is as close as you can get from taking a picture of a certain star and see if there is an exoplanet around it, and it will appear as a bright spot. And the difficulty in that technique is that the difference of brightness between the star and the planet is huge. It's orders of magnitude, so it's very difficult to see such a small signal. And each of these techniques has a certain sensitivity. So for example, the transits, they are very good at detecting planets which are close to their star. And so most of the planets we know are actually known from transit. But you see, it's very easy to see that if the planet is very far, its transit probability is very low. The probability that it will pass right between the observer and the star is very low. So it will not be very good at detecting planets with a period greater than, say, 100 days. With imaging, you can detect planets with very, very long periods, like hundreds of years or thousands of years even. But if the planet is too close, there is the contrast is too problematic. Okay. So now what do we do with all these planets? We are trying to understand the internal structure and the atmosphere of planets. We want to understand planetary formation, and we want to search for life. So this is sort of the geography of planets, and this is sort of the history of planets. And so to understand the internal structure and the atmosphere, we need mass measurements, and and mass measurements are very, very useful to constrain the density. For example, if you have the radius by the transit technique. You can also observe the atmosphere of the planets with the spectroscopy, either with the reflected light on the atmosphere of the planet, or with the light passing through the atmosphere of the planet when the planet transits. To understand planetary formation, you would typically study the statistical distribution of the planets and compare it to the outcome of formation scenarios and see if the scenario that you envision reproduces the observations. And of course, we want to search for life outside of the solar system. And so for that, we need to detect planets in the habitable zone where water can be stable in a liquid form. So it has to be not too hot, not too cold. And obviously, we want to observe the atmospheres of these planets to detect the presence of certain chemical compounds, which are indicative of the presence of a biological process. For example, oxygen, ozone, methane could be indicative of the presence of life. So let's focus a little bit more on the radial velocity technique. So the principle is also very simple. You have a star and an observer here, and you use a certain device to spread the light in a continuous spectrum. This device is called a spectrograph. So obviously, in real life, it's more complicated than the prism. It's in a controlled environment with it's in vacuum, it's controlled in temperature, and hence the container around the instrument. And why is this technique important? So it measures the mass, and the mass is essential, as we said, to understand the internal structure of the atmosphere, because it gives the density, and for the atmosphere, it gives the surface gravity of the star, which is very important to determine the atmospheric scale height and study the atmosphere. We need also the mass to understand planetary formation, and the RV has another advantage over the other techniques, which is that it can detect misaligned systems. So suppose that here you have a star and you have a planet which transits. Here, if the other planets do not transit, you will never see them with the transit technique. And well, not never, because you can have transit timing variation, but in most of the cases, you cannot see them. And so if you want to detect all the planets within the system, which is very important to have a broad view and understanding of a particular planetary system, you need to use RV, at least to detect small planets. And to search for life, also, you need the masses, and you need the RVs to detect exo-Earth around stars which are close to the solar system, so we can characterize them better with the future missions. So here you see the different detection limits of the different methods in semi-major axis and mass. And you see that with the current methods of RV, we have a precision on the velocity of the star of 1 meter per second. And it's not sufficient to get to the Earth or to Venus. And what is preventing us to do so? Well, let's try to understand a little bit better the radial velocity signals. So suppose that you have a planet orbiting the star. So the star has a reflex motion around the center of mass of the system, and you see that the spectrum is shifting. From this spectral shift, you extract the velocity. And what is the velocity that you expect? So if you have one planet around the star, this is the type of signal that you should expect. If you have several planets around the same star, you will basically have the sum of the different signals. So you will have a sum of different quasi-sinusoidal signals, periodic signals, and the amplitude of a certain component is proportional to the planet mass. So, and the shape of these signals is such that if the planet has an orbit which is nearly circular, then the radial velocity will vary as a function of time in a sinusoidal manner if the planet is circular. If it's eccentric, so if the orbit is a little bit elongated, then most of the signal will happen when the planet is close to its star. So, and even more so if the orbit is very eccentric. So in that case, when the planet is far from the star, pretty much nothing happens. You have a very small variation of velocity. But then when it passes close to its star, then the star accelerates, and you have a very important bump in velocity. So you should look for the signal at this particular time. And more precisely, you can describe the radial velocity time series as a sum of such signals, which are described by this equation. Each of these signals is described by 5 parameters, including its period, its amplitude, and its eccentricity, so how much the orbit is elongated. And what makes our life difficult is the stochastic term, the noise term. And the noise in radial velocity is particularly complicated. First of all, you have obviously the photon noise. So when you take a measurement involving light, the emission of light is a fundamentally stochastic process. So the measurement is fundamentally stochastic, and you will have an error on your radial velocity measurement, which is associated to the fact that you have a limited amount of photons. But now you also have instrumental effects, and here is a representation of the radial velocity in meter per second as a function of time of reference stars monitored by the spectrograph SOPHY. And these stars are deemed to be stable without planets, and the different blue points, they don't even correspond to the same star. So what we are seeing here as a function of time is a drift of the 0 point of the spectrograph. And you need to, so in instruments like SOPHY, you do need to monitor this variation of the 0 point due to the, for example, to the aging of calibration lamps, or to the change of a certain component in the instrument. And so, but you also have other instrumental effects which affect your data. And most importantly, you have stellar effects. So radial velocity is fundamentally a Doppler measurement. So you are measuring the velocity of photons coming towards you. But so if the star that you observe was a perfectly uniform sphere of light, then you would have the part that is blue shifted because it's rotating towards you, and the part which is red shifted because it's moving away from you. So each of these has a specific Doppler shift. They would cancel out. But you have spots on the surface of stars, yeah, and you have bright areas. So it breaks the imbalance of the approaching and the receding limb. So it will create a stochastic variation because these spots, they appear stochastically, they appear randomly. And it will create a random noise with a strong power at the rotation of the star and its harmonics. Now you have several other processes at the surface of the star, for example, granulation, which is caused by the convective motion of the gas, and which creates also a noise with a certain temporal structure, which is characterized by this power spectrum density, and with several bumps, which are due to different phenomena at the surface of the star. So just to show you how much stellar activity can be a problem, here in red is simulated data with 3 injected signals and sampled with a realistic radial velocity sampling. And when you look at the periodogram of this time series, then you see 3 very clear peaks corresponding to the injected planets. You have secondary peaks, which are due to the fact that you have an incomplete sampling, so you have an aliasing phenomenon. But now, if you simulate on top of that the stellar activity, you get the blue periodogram / Fourier transform, and which is completely dominated by low frequencies, and which has some power here, which is the rotation of the star. And you don't see at all the different the periods of the injected signals. Okay, so basically we have a problem of time series analysis. Here is an example of some radial velocity data of velocity as a function of time, measured velocity as a function of time. And here you have also several measurements as a function of time for another star. And these are typical data sets that we are trying to analyze. They are unevenly sampled, close to one-day sampling. You have typically 40 to 1,000 data points, and they are corrupted by very complicated noise. Now you want to determine how many planets you have and what are their orbital elements. and so to give you a hint of how complicated this is going to be for Earth, in blue you have the signal which is expected from the Earth, and in black you have the radial velocity measurements which are observed on the sun, on our sun. These are real measurements of our very sun that we are trying to monitor to understand typically these complex stellar noises. And we want to extract the blue signal from the black data. Okay, so now if we are trying to model what we are trying to do in a statistical sense. So we have an estimate of RV, and it's going to be the sum of the RV, which is due to the actual motion of the center of mass of the star, because it's moving in a barycentric frame, plus these contaminating signals. And you have also the inevitable measurement error. And but the thing is, RV is only the RV, which is due to the motion of the center of mass, is a pure Doppler shift. So it's purely affecting the spectrum as a shift, as a translation of the spectrum. Now the RV, which is contaminating the signal, affects also the shape of the spectrum. So now let's take a look at the average spectral line. So this is the intensity of the flux as a function of the wavelength. And when you look at the problem of the granulation, you have so this is a close-up of the surface of the star, and you have these cells, these convection cells with bright gas at the center, which is moving outwards, and darker gas, so cooler gas at the edge of the cell, which is moving towards the star, which is to the interior. So when you look at the Doppler signature of these two regions, of the granular region, the outward moving gas and the inward moving gas, their average spectral line will be like this. And it means that the combination of the two, the sum of the two, will make a skewed spectral line. So if you monitor the skewness of the spectral line, if you monitor its width, then this might change due to the granulation pattern, but the planet would just act as a translation of these two intergranular and granular lines. And so if you see a signal in the RV here, which has also a counterpart in these indicators, then you could say that it's due to activity and it's not a planet. So in practice, what you would have is the time series of RV signal. And for each spectrum measurement, you will also have the skewness of the line as a, so here, each point corresponds to one measurement. And the full width alpha maximum, so the average width of the line. So RV now is a problem of multi-variate time series analysis. And in Bayesian terms, it means that you're trying to infer the parameters of the planets and the parameters of other processes which are linked to the star, for example. And so in full generality, you would base your reasoning on the full data set, so the full time series of spectra, everything that you have at your disposal, but you reduce this spectra to a few time series, the RV time series and the indicator time series, and then you have several problems. So how do you reduce this information? How is it efficient to reduce? How can you do it efficiently? Now, if you write explicitly the base formula, you will have to specify this particular model. So what is, knowing the parameters of the planets and of the star, what is the variation of RV and of the indicators that I expect? And so now that you have that you have your model of the posterior probability, you have a decision problem. So based on this, how many planets do I claim? What are their orbital elements? And finally, for each of these subproblems, you need to be able to compute everything, and you are manipulating data sets which are so one spectrum, for example, has 40,000 entries, and the time series of spectrum can be quite huge to manage, especially because the model is so complicated. So if you're interested in learning more about the statistical framework for RV analysis, I have an upcoming review with Eric Ford of Penn State University. So you have these four problems: reduce the data, model it, compute everything, and then based on these computations, decide what you want to do. And here I'm going to talk about these two aspects. So obviously these aspects are intertwined, but for the sake of this talk, we're going to assume that they're separated. Okay, so let's move to the optimal detection criterion. So what people do usually is either to compute a periodogram or use Bayesian techniques. What is a periodogram? So the principle of a periodogram is to look at a grid of frequencies, and for each frequency in the grid, you fit a sinusoidal signal, and you see how well you can fit the data with it. So if you fit very well the data, you have a high peak. If you fit perfectly the data, the peak is going to be equal to 1. And if you don't fit anything in the data with this particular frequency, then the value of the periodogram is going to be 0. And so you would say that if the peak is sufficiently high, so if the null hypothesis would generate a peak at least as high as this one very infrequently, the probability is very low, then you would say that, okay, this peak corresponds to a real signal. But the problem is you look for only one planet at a time. So if your sampling is too sparse, and it's often the case with RV, you can have this situation where here you have 3 planets with equal amplitude, which are marked by the red stems. And so these are the periods and the amplitude of the signals. And the maximum of the periodogram does not occur at any of the true planets injected in the system, in the data. So it's something that you want to avoid, obviously. Now you can search for several signals at the same time, and typically you can compute the Bayesian evidence of the n-planet model. So you would compute the integral of the prior, knowing that you have n planets, times the likelihood, knowing that you have n planets, over all the possible combination of n planets, which are represented here. With the variable theta. And you would say that you have a planet if the evidence of the n+1 planet model is greater than the evidence of the n-planet model by a factor of 150, or preferentially even higher, 1,000, 10,000. Okay, but now we can try to ask the question, okay, so this is what people do, but what if we were trying to determine an optimal exoplanet detection criterion? And if we want to do that, we need to ask 3 questions. So what do we mean by an optimal detection criterion? Once we have defined the problem, what is the optimal solution, and how does it perform compared to other detection criteria? And so all the details are given in those 2 references. So what do we mean by optimal detection criterion? So the context I'm going to use is this one. So I have some data y, and I have some parameters theta and eta. So y is my data. Theta j is the orbital elements of planet j, and I have n planets in the model, and n is unknown. I don't know how many I have. And here I put everything else. So I might have instrumental effects which are parameterized, for example, offsets, intercepts, trends. You might have parameters which describe the noise properties, which describe the covariance of the noise, and you put everything in this eta parameter. And I'm going to define a detection claim as I have n planets. One of these planets has orbital elements in this region of the parameter space. One planet has orbital elements in this region of the parameter space, and so on. So, but everything I'm going to say is valid in a much more general context where I have the data which is described by n patterns. These patterns all have the same parametrization. And the data is corrupted by nuisance signals, which are described by nuisance parameters. And a detection will be, I have n pattern, one pattern with parameters in there, one pattern with parameters in there, and so on. So in the case of RV, here my parameters are the orbital elements, and I'm going to say that I'm going to detect planets if I have a certain accuracy on their orbital frequency. So the frequency at which they orbit their host star. So suppose I claim the detection of two planets with this. So I will say there is one planet with orbital frequency within these two bounds, and there is another planet with an orbital frequency within these two bounds. But in truth, there are three planets. There is one here, and this one I claim correctly this detection. So I have one correct detection. But now I claim that there was a planet with an orbital frequency in this range, and there is none. So I have a false detection. And now I have two other planets which do not belong to any of the intervals that I have defined, and this corresponds to missed detections. You can also define the missed detections in another way, which is saying that you have claimed that there are two planets, but in fact there are three. So in that case, you will count one missed detection. But in fact, the optimal detection does not depend on the particular definition of these missed detections. You can define it one way or another. It's still the same. It's still the same or almost the same solution. Okay. So now we have defined what is a detection criterion. What is my detection? And now we need to define what we mean by an optimal detection criterion. So I have defined false detections, I have defined missed detections, and just like in the first case that I showed, I'm going to define a cost function, which is the number of false detections plus a certain cost for the number of missed detections. And I want a decision rule selecting the regions of the parameter space, which minimize the number of false detections and missed detections. There is another way to look at things and say, well, I want to minimize the expected numbers of missed detections, but I don't want too many false detections. So I am going to put a hard constraint on this number and minimize the expected number of false negatives. And here, when I'm talking about mathematical expectancy, it's taken on the posterior probability of the parameters of my models, the orbital elements of the planets and the nuisance parameters, or the parameters of my patterns and the nuisance parameters describing the data Y. So now, how do you compute this cost function? You need to break down your parameter space in several subspaces. So you're saying I have detected n planets. Okay. Now suppose that in fact there are zero planets. So I have n false detections because there is no planets. I claim that there is one. They are all the detections are wrong. Now suppose that there is one planet. So either I have at least one correct, or I have zero which are correct, and these correspond to different weights of the utility function, and so on. So okay, suppose that in fact there are k planets. Suppose that in fact there are more planets than I claimed, and when you rearrange all the terms, you end up with this expression. And here the important term is this one. It's the number of this is the probability mass of the regions corresponding to J correct detections, and you want to favor it. So the more false detections I have, the more true detections I have. Sorry, the more true detections I have, the more I want to favor it. So if I have J true detections, my utility is going to be pushed by a factor J. Okay. And now what is going, so if you were to try to maximize this function, you need to explore all the different combinations of parameter space. So you need to explore all the combinations of choosing one region of this parameter space and moving it around, then two regions and moving them around with all the different possibilities, and so on. So it's quite computationally demanding. And where you need the theory is to try to reduce the space of the search to say, well, actually, I'm going to find very quickly what are the regions of the parameter space where I have maximum probability. And you have one result which helps you greatly to do that, which is if the region of the parameter space that you take are disjoint, so if you forbid to claim detections on overlapping regions, then this sum is just equal to the individual probability, posterior probability to have something in there. So now, instead of maximizing this function, you are just trying to choose the different regions of the parameter space which maximize the sum of the posterior probability to have a pattern in these regions. Okay, and what is the optimal solution? So if you get rid of these complicated cases where you claim signals which are very close to each other, and if you say, well, actually my prior information forbids two signals to be too close to each other, then everything becomes super simple and extremely intuitive. So in that case, even the two problems that we define in terms of cost function or minimizing number of bits detections with a constraint on the expected number of false detections, both problems have the same solution. And what you would do is simply to take so in the case of exoplanets, you would have your frequency interval, which defines the frequency resolution you want on your planet. You slide it across the orbital frequency range, and you want to compute the probability that there is a planet with frequency in this interval, knowing the data. And this, I call it the true inclusion probability. And the false inclusion probability, in analogy with the false alarm probability, is the probability not to have a planet in this range. It's simply 1 minus the true inclusion probability. And so this is an application to a real data set. So I analyze my RV dataset and I slide my frequency interval across the orbital frequency range, and so here I have a very weak signal. Then I move it still, and at some point on a certain interval, I have a very high false inclusion, true inclusion probability. And I represent it this way because if I represent the log 10 true inclusion probability, I will not be able to distinguish signals which are very significant or extremely significant because they will all be stuck to 1. It's like the difference between 0.999 or 0.999999, you cannot see it on this graph. But now if you represent as well the minus the log 10 false inclusion probability, you can see that this signal is significant. The probability that this signal is not present is 10 to the minus 13, and here it's only 10 to the minus 4. So it's just a convenient representation to differentiate signals which are very significant from those which are less significant. And I call this particular figure a Fieb periodogram. Now, how would you do it in practice? How would you compute this probability? Well, you would compute it knowing that there is k planets. So you explore your model with a fixed number of planets, but then you average over the posterior probability that you have k planets at all, which is simply given by reweighting the marginal likelihoods of the different k planet models. Okay, and in fact, if you have already a Bayesian evidence calculation method, these are just byproducts of this evidence calculation method. So it's just a post-processing method. You don't need anything new compared to a classical Bayesian method. And for this particular example, I used the nested sampling algorithm, which is called polychord. Okay, now to speed up, well, I'm not going to talk about this. It's, yeah, so one of the problems that you have with the false inclusion probability is that you need to define the maximum number of planets, because otherwise you cannot compute this sum or the weighting that you will apply to the k-planet model. So first of all, you want to rerun your algorithm for a fixed number of planets, because the calculations are stochastic. They will be done either with the MCMC or with a nested sampling algorithm, and the estimate is noisy. So you want to see that by rerunning it, you still get the same result. And now you can increment the value of the maximum number of planets and see if the periodogram changes at all or not. And if your decision stops changing when you add more planets, it just means that the probability that there is more planets than what you already have is very low, and you don't need to add more planets in the model and keep computing this very heavy posterior probability for a model which is more and more complex. So now, how does it perform? So I'm using a simulation. I simulate 1,000 systems with 0, 1, or 2 planets, and they are generated on 80 timestamps coming from a real data set. I choose certain priors for the orbital parameters, and I'm going to analyze it with the correct priors, but just varying the different detection methods. So for example, I will use a periodogram, and I will compute the periodogram of the simulated data, take the highest peak, see if it's significant. If it's significant, I fit the corresponding signal, I remove it from the data, and I search for another signal with the periodogram. And if the signal is significant, I will add it to the detected planets. I will do it also with sparse recovery techniques that I developed during my PhD, where here I'm searching for all the Fourier components at the same time, but I have a sparsity constraints, an L1 constraint, which pushes for a sparse solution. And so in that case, for example, it will spot correctly the true periods of the injected planets represented in red. So for this particular system, for example, I would say that there is a planet in there within this frequency range, and I would be wrong. And with this method, I would say that there is the planet in this frequency range, and I would be right. And so now if I count, as I vary the detection threshold, so the false inclusion probability detection threshold, the base factor detection threshold, the false alarm probability detection threshold, I will have a certain number of mistakes, so false plus miss detections, as a function of this detection threshold. And so obviously, the more stringent I am, the more I want to be sure about the planets, the less false detections I will have, but the more misdetections, because there is a lot of true small amplitude signals that I will reject because their statistical significance is not high enough. And so now if you want to compare the different methods, you can compute the total number of mistakes as a function of the number of false detections. So it's a sort of ROC curve, but the ROC curve here would not really be appropriate because the normalization would be a little bit messy. So now what's interesting is that in two different settings, either high signal to noise ratio or low signal to noise ratio, the false inclusion probability gives me a smaller number of mistakes, so a smaller number of misdetections for a given tolerance to false detections. And by quite a lot, in fact. I can get 30% more planets with still maintaining a very high confidence in these detections, just by changing the way I analyze the data. So the model is exactly the same. It's just a matter of a statistical significance scale. Okay. And I think that one of the very nice advantage of detecting signals based on this criterion instead of the base factor is that it's much easier to interpret. So suppose that I have n detections with the same false inclusion probability, for example, or true inclusion probability. So suppose I have 1,000 detections with a true inclusion probability of 50%. It means that approximately 50% of the detections should be true and 50% should be wrong. So now I can look in my simulations. Well, in 50% of the cases where I said that there is a 50% chance that there is a planet, well, there is a planet in 50% of the chances, in 50% of the cases. If I say that there is a planet with a 95% probability, well, on average, it means that 95 cases out of 100, I do have a planet. And so it's even something that you can use to calibrate your probabilistic model, because if your probabilistic model is correct for the data, then by analyzing a large amount of data and then waiting, let's say, 10 years and see whether there were truly planets or not, then you could calibrate, you could cross-validate your probabilistic inference. Okay. Actually, I'm going to stop here because that's mostly what I wanted to say. I'm not going to talk about the computational methods because it's getting late. Yeah, so basically, my point to the exoplanet community was, yes, we use Bayes factor, and this is very good, but I mean, for this, using exactly the same kind of computation, you can reprocess the outcome of your computations to have a detection criterion which is much more efficient. And I think we can make a case that basically when you compute the probability of what you are interested in knowing the data, it's very hard to beat. And you have a lot of Dutch books, example, which show that, in fact, that's what you should be looking for if you have the computational means to do so. And the last point that I want to make is that, obviously, just like the Bayes factor and just like any other type of probabilistic inference, the result heavily depends on the model. And this criterion is only optimal if the model of the data is appropriate. So I think it's very important to average over different models, especially of the stellar noise, and to check the residuals once you have operated your model to see if at least your model is consistent with the data in an absolute sense. And that's my concluding remarks, and thank you for your attention.